Welcome to the course, everybody. Almost the last course. Today we're going to talk about more cascades. First, I want a moment of silence for the people of Ukraine who are fighting for their freedom and for ours. Before talking about cascades, I want to finish what I promised last week. Remember this formula? This is what happens when you have a sequence of decisions, okay? So the probability that the world is good, given this sequence of signals, is this huge formula, where P is the probability of the world being good, Q is the probability of the signal being good, the high signal, the world is good. So we know that Q is bigger than half. And we know that we have more high signals than low signals. So what is this number compared to the probability of G? What is the probability of G given signals S compared to probability of G? This is P. Probability of G, this is what we call P. So we know A is greater than B, and we know Q is bigger than a half. Now, this is the kind of algebra estimation that is important that you do. Okay, so I will take this formula and I will show you that this is, if A is greater than B, I will show you that this is greater, that it gets bigger. Okay? We'll see how it works out. So, first, let me take a look at the denominator here. 1 minus, so this is very complicated. So I want to simplify this. Okay. So 1 minus P, 1 minus QA, QB. Q to the B. Now I want to simplify this. So in one way to simplify, I replace this 1 minus Q by Q, and this Q by 1 minus Q. Now I know that Q is bigger than a half, and I know that A is bigger than B. Okay? So that means A is bigger than B. Here I have B's, B, Q, B, Q's, and here I have A, Q's. Oh. But if A is bigger than B, and here I have A, 1 minus Q's, and B, 1 minus Q's. I notice A is bigger than B, so these guys will become less. There will be less of the 1 minus Q's, and there will be more of the Q's, right? If you compare these two, more Q's, and since Q is bigger than a half, so A, that's because A is bigger than B, yeah? So the 1 minus Q's here, there's A of them, and here there's only B of them, and A is bigger than B, and here I have more, so I have less 1 minus Q's and more Q's, right? And Q is bigger than a half. So what does that mean? I have here some numbers. bigger than a half. So a certain number of guys bigger than a half. And here I increase those. And the smaller numbers, less than a half, are decreased. So I increase the bigger numbers, and I decrease the smaller ones. Oh. So what does it mean? It means that this one will be bigger than this one. Huh? Here I have, for example, if a is equal to 2, and b is equal to 1, I have here 1/2 to the power 1, 1/2 to the power 2. But here I will have something less than a half to the power 2, something less than half to the power 1. So I have less of these and more, so more bigger numbers than smaller ones. So this will be bigger. Okay. So if I replace this by this, the denominator here, the denominator gets bigger. Okay. So that means this number gets smaller. Okay. And so you can take this number and add it now to this one, and you see that the p and the 1 minus p cancel out, and you have q to the a, 1 minus q to the b, so it's equal to p. Okay? What does that mean? It means I have replaced this by something that is equal to p. Okay? But I have made it smaller by doing that. You see? You see what I'm doing here? So I add this now. So I've made the denominator bigger, and the whole thing simplifies to p. That means I've made the number smaller, and that smaller number is equal to p. That means the original number is bigger than p. Okay? Right? Okay, I think that should be clear enough. If it's not, you can work it out. Okay. Okay, let me go now to today's lecture. Today, I want to talk about something which is called direct benefit cascades. It's also called network effects. But network effects is not actually such a good name because it seems very general. It could be anything. What is network effects? But actually people call this sometimes network effects. But a better name is direct benefit cascade or direct benefit effects. It means that if you do what everybody else does, you get a benefit. If everybody is using Microsoft Word and you use Pages or some other weird processor, then you have no benefit because you cannot exchange information. But if you use Word, you have a benefit because it lets you easily exchange information. So if you align your decision to other people, you get benefit. So we're going to analyze this today. Okay? Also, maybe if we have time, I'll talk about power laws today. But the first thing is direct benefit. And this, if you want to start your own internet company, you'll see this is very interesting and very important. Okay, let me first give you some intuition. So the point is, you're making decisions on something, and a whole bunch of people are making decisions too. And how do you make your decision? Last week we saw what I can call informational effect or information cascades if the decision is made sequentially. So that's what we saw last week. But today we're going to see another kind of effect is when your decision, it helped if you align, if you have the same decision as others. And so some examples is fax machine, which used to be a big thing. It still is in Japan, it seems. So if many people have fax machine, then it's useful. Otherwise, it's not useful. Or social networking, Facebook. Facebook is nice because many people use Facebook. You were the only one using Facebook would not be so interesting. Or operating system, Windows, Mac OS. If there's many users, there's benefit, because there's more software, more applications, there's more updates, and so on. Word, for example, Microsoft Office. So you can see there's usually a benefit. And we're going to analyze this today in a very concrete way. With models, as usual, and very different kind of model than we did before. Okay, so this slide is just to introduce, is just connecting what I'm doing today with economic theory. If you read books or paper on economics, they will have this word called externalities. So network effects for economists, it's called externalities. Okay. Positive externalities means you get a benefit if other people are doing it, and negative externalities, where if many people do it, there's a disadvantage, like traffic congestion. If many people go on those roads, more people, you have more traffic congestion, so it's bad. So that's a negative externality, and the positive externality is the same as a network effect. Okay, so this is just to make the connection with the terminology that economists use. And economists also have this notion of the effect has to be uncompensated. That means if you drink a can of Coca-Cola, so theoretically that means there's one less can for everybody else, but that's not a problem because since you're paying for the can, Coca-Cola company will make another can. Okay? So the effect is compensated. So this is not an externality. Drinking more Coke will not give you a benefit because many people drink Coke. Okay? So the fax machine is an externality. Okay, so that's just to make the connection with economists. Okay, so what are we going to do today? As usual, you get the idea by now. I'm going to define a formal model, which is simple, idealized. We're going to analyze it, and then we get lots of good intuition. Okay? This model will be about markets, buying and selling. If you remember, we already talked about markets before. Remember matching markets, where you have something called market clearing, which means supply equals demand. And we made a discrete model with bipartite graphs. So that was a discrete model. So we did this one before. But today's model will be very different, even though the first model will actually be kind of the same one. It'll be supply equal demand. But today I'm going to show you this really interesting kind of continuous model, using real numbers and real functions. Okay, so we're going to make 4 models, and they're step by step. They get more and more interesting. The first one is just the base case, supply and demand, no network effects. You have a product and you buy it, and what is the price? So there's some equilibrium effect. So this is just introducing the formalism. Okay. The second model is we're going to add a network effect. Okay. When you add more users, you increase the value. So that's the network effect. And the third model, we're going to make it dynamic. We're going to see what happens in time. So that's interesting because in time you can have instability, stability. Maybe the whole thing goes bad after a while, or maybe it converges to a good situation. So that's time. We're going to make it more dynamic. And the way to do that is that the users, they don't know how many people are using. They have some guess, and the guess improves over time. So this gives you this dynamic effect. And the final is the most realistic one. This is where you have both network effect and individual effect. It means the decision or the product is good when you're the only one using it. It's already good. Okay? Like if I buy Microsoft Office, even if nobody else uses it, it's still useful. I can write text and so on. So it's called individual effect. It's already good by itself. But there's even an improvement if many people use it. So the final model is we're going to have a model where we have both. So this is the most realistic one. we're going to talk about stable and unstable equilibria and tipping points. So you're going to get some intuition about how things evolve and how things can become stable and unstable. Okay? So it's all actually quite interesting. Okay, so the first model is just the basics. Economy without network effects. Okay? In the first model, we have a model. So here, this is a continuous model. So you have to put your mind on how now we're going to model the economy in a very different way as before. Okay? So we have consumers and we have producers. The consumers are real numbers from 0 to 1. So we assume there's a whole bunch of consumers and each one of them is some number. 0.01 is a consumer, 0.02. So all the real numbers from 0 to 1 are uniform names of the consumers. So that's kind of weird, huh? So the consumers are uniformly distributed from 0 to 1. So the interval from 0 to x contains x fraction of consumer. That means 0x has the x is a name of a consumer, but it's also the position of the consumer on this interval. Okay? So the idea is that this is a continuous approximation to a very big market. Very large, finite. I guess usually the consumers, it's this finite number up. And each consumer's decision whether to buy or not does not have so much effect. Okay? So there's a bunch of consumers going from 0 to 1. And each consumer has a number which is the maximum price that he wants to pay for the product. And this is called the reservation price. So it's not the price he actually pays, but it's the maximum he's willing to pay. So that's a function, R of x. Okay? And now, the funny thing, we're going to arrange the consumers. So we put them in this uniform from 0 to 1, but we're going to sort them. We're going to put the consumers with the high reservation prices, we're going to put them earlier. So the low number of consumers are the ones willing to pay the most. Okay? So this is a very curious model, but it's very powerful. So if x prime is less than x, so these are names of consumers. They're real numbers, but they're also names of consumers. So if x prime is less than x, then x prime wants to pay more than x. Rx prime bigger than Rx. And the nice way to see this is as a graph. Okay? So here we have the consumers going from 0 to 1. So each point on this line is a consumer. And the ones that want to pay a lot are on the left. Okay? And here on the right are the ones that don't want to pay a lot. And then on the vertical, we have the prices. And this line, this curve here, is the function R of x. So low number of consumers are willing to pay a lot, but as the consumer number gets higher, they're willing to pay less and less and less. Up to 1. So the last consumer is number 1. So they only go from 0 to 1. Okay? So suppose now the price is P. Here, the price is P. That means this horizontal line, y equal P, will intersect the curve at some number x. So we're assuming that R is some strictly decreasing function starting from maximum R0 going to minimum R1. We assume that. And the price is P of the good. That means all the consumers from 0 to x have a higher reservation. So they all are going to buy. They're all going to buy. But all the ones to the right have a lower price they're willing to pay, so they're not going to buy. Okay? So all consumers from 0 to x will buy. And you can even see the fraction of consumers that buy is x. If this is 0.2, then 20% of the consumers are going to buy. Okay? So this is a model of an economy. You see that? And depending on the price, if you know the function R, you can see how many people will buy. If the price goes down, more people will buy. If the price goes up, less will buy. Okay? So you get this model. We're going to use this the whole course today. Yeah? It's going to be variations on this model. Okay. Now let's talk a little bit economics, how it works with companies. We're producing something, which is mobile phones or something, so the cost of production is P star. Okay, and let's say there's many companies producing, so they can produce any number of the good at price P star, but they cannot produce at lower price, because this is the cost of production. They're not going to produce when they lose money. Yeah? So the price will stay at P star. It will not be higher because of competition. I remember we saw when we have traders, when we have perfect competition, it reduces the two to get to sell their product, they will both reduce. So if you have lots of producers, the price is going to go down, and in the model it will be exactly P star. Okay? Because of competition, the price will not be above it. So this is a nice market where competition is doing the nice thing. It's reducing the price. There's no monopoly or something in this model. So this is going to be the price, and the equilibrium quantity will be this intersection, will be X star. So this is how the real market's going to work. Basically, it depends on the cost of production, and if we know the function R, we get this equilibrium. So this is an actual equilibrium. Okay, so there's something dynamic here. So if this number goes down, okay, but then if it goes like here, these consumers would not buy. But that's not going to happen. They have higher reservation price, so they will buy. So if this number tries to go down, there's going to be upward pressure, is what economists would say. There's going to be these guys then who will buy. So it pushes back X back up. Okay? And if X star goes higher, then X goes higher than X star, then we have some consumers with a lower reservation price. So they're not, in fact, they're not going to buy. They're going to be unhappy. Say, why am I buying? I'm losing. So it pushes the X down. So this is like a stable equilibrium point. Okay? It will not go up or down. If there's any fluctuation of this, the market will tend to make it go back. You see that? So that's important kind of intuition. So today we're going to be using that kind of intuition. What happens if the number changes a little bit? You have this pressure going up and down. Okay? Okay, let me just say something about what we saw before, about social optimality. So you can actually compute, is this equilibrium socially optimal? Remember social optimality in game theory? Social as choice of strategies. So here the strategy is, for each consumer, it's either buy or not buy. So all these consumers are players, and they all can decide, buy or not buy. And that's the game. Okay? And social optimality is if the sum of the consumer's payoffs is maximum. So what is the payoff here of a consumer? Well, actually, you can see the payoff as the difference between R of X and P star. So R of X is what the consumer wants to pay, but P star is what the consumer really pays. So the payoff is like the difference. The consumer will have some benefit personally. You say, look, hey, I have to pay less than what I think it's worth. So the payoff is Rx prime minus P star for any consumer. So if you go from 0 to X star, the total social welfare is actually the area under this part of the curve. Okay? In fact, there's also a negative social welfare here, but you don't count this because these guys are not going to buy. So they will not have negative payoff. Well, that's stupid, huh? They will just not buy it, and they will have zero payoff. So here, if you would count these, that would make it go negative. But we're not counting them because they're not buying. Okay? So it's, in fact, it's actually the integral from 0 to x star of Rx minus P star dx, if you want to make a formula. So this is, you can actually connect this to game theory and social optimality. Okay? So that's just a little comment on the model. So you understand the model, huh? Okay? So that's the first model. I just introduced it. Now let's add network effects to this. Now we're going to add these benefits, these direct benefits. So we're going to make the model a little bit more complicated. Okay. If a potential consumer, so a consumer wants to decide to buy or not, they will take into account their own reservation price, their own R of X, but also the total number of buyers. Okay? And we assume that all the consumers, all the customers, they know what fraction are going to buy. So now there's actually two functions. There's a new function here. So this is interesting. It's important to understand. So R of X is for each consumer X is how much they want to pay, maximum. But there's a new function, f of z. Z is the fraction of all the consumers who have bought the product. Maybe 90% have bought Microsoft Office. So Z would be 0.9, okay? And f of z is the benefit to each individual consumer when Z have bought the product. And so we can make a final formula. When does a consumer decide to buy? The consumer will buy not just if R of X is bigger than P, but if R of X times f of z. So this f of z is the network effect. Okay? It's the benefit of how many totally are buying. And we multiply them to get the actual price. So this f of z is like how much the benefit the consumer gets. Okay? Now, we assume now some things. F of z is increasing in z. We'll assume that when more people use the product, when z is higher, it gets them higher. Okay? Well, let's assume that. It's also a multiplication, not an addition. We're going to assume it's actually multiplying here, and not Rx plus f of z. Yeah? It's multiplying because people with a higher R of X will benefit more. So if Microsoft Word is worth 10 million euros to me, I will get more benefit than if it's only worth 25 cents. Okay? So it's actually a multiplication. Okay? We also will assume f of 0 is equal to 0. In this particular case, if nobody purchases it, we'll assume the benefit is 0. So that's like a fax machine. Huh? If you're the only person with a fax machine, you cannot send a fax to anyone. Or it's like telephones. Huh? If you're the only person in the world with a phone, it doesn't really help. If you're using it for phoning people. Maybe you can play Tetris, but we're assuming it's an actual phone. Huh? So we assume f of 0 is 0. And we assume also it's a continuous function. It's not jumping. So this is a simplified, ideal kind of model. Huh? Okay? So you see these idealizations, they allow us to analyze things, but they also will give us really nice intuitions. We're also going to assume R of 1 is equal to 0. This is for simplicity. That means that there's some consumers who only will pay very little amount. Some consumers, they will not pay more than 1 cent for Microsoft Office. Okay, we'll assume that. that there's some consumers who will only pay very little. That's also for keeping things simple. Okay, this is so that we can analyze things. Okay, so let's analyze. Let's start analyzing this now. Okay? So all consumers expect that the fraction buying the product is Z. So they all know that. Everybody knows that 90% of the users are buying Microsoft Office. So if that's the case, the fraction that actually purchases will also be 90%. Okay? So if you can actually reason on that, if you know it, everybody knows that 90% will buy, then the actual percentage is 90%. This is called a self-fulfilling expectations equilibrium. Okay? It will not be more than 90% because those ones will lose money. It will not be less because you will have extra ones who can come and get money, who can get a benefit. So in this model, that the fraction actually purchased will actually be Z. It will be the same as the total buying the product. You see, it's kind of a circular dependency, yeah? So we can actually look at it a little bit more closely. So if everybody expects Z equals 0, so assume Z equals 0. Okay? If everybody expects that nobody will buy, then R of x times f of 0 is equal to 0, and that means nobody will buy in the model, okay? Because they will only buy if this number is bigger than the price. So it works for Z equals 0. What happens if Z is strictly between 0 and 1? Okay? So if a consumer x prime is buying, and if x is less than x prime, then x will also buy, because R of x times f of z, this is the price, gets bigger, because R of x gets bigger when x is small. Okay? So the set of purchasers is exactly the consumers from 0 to x. Okay? And the price is the lowest one. It's price of consumer number z. So the actual price will be R of z times f of z in this model. Okay? In this model, the equilibrium price is R of z times f of z. So you can see that this idealized model, it lets you actually reason about things. Of course, you have to know these functions. You don't always know them. Okay? So, therefore, we have two models. We have the basic model, where you only have the price, the first bullet, and the price equilibrium will be R of x star, which is the production, corresponding to production cost. And in the model with network effects, the price would be R of z times f of z. So you can actually figure out z from this. Okay? So without network effects, if you lower the price P star, the number of consumers will increase, right? You have this function, You have this function that goes down. If you lower the price, the number of consumers increases, Right? That's the first model. You see that, That's the first. But in the second model, what happens if you lower the price? Well, now we have a more complicated equation here, What's so simple? So there is actually an equilibrium for z equals 0. Nobody buys. But what about other equilibria? Now it starts getting interesting. Because this equation is more complicated now. You have this product. And what we're going to do now is we're going to make some assumptions. We're going to assume R and F have certain function, and we're going to see what happens. And this will give us a really good intuition. Okay? So here is a typical kind of example. Let's say that R of x is equal to 1 minus x, Let me make a picture. So here we have consumers going from 0 to 1, and R of x, let's say very simple, it's 1 minus x. Okay, we know it's a decreasing function. We know R of 1 is equal to 0. We know R of 0 is some maximum price. But just for simplicity, let's just say it's linear decreasing. Okay? And now let's say f of z is equal to z is linear increasing. We know that f of 0 is 0. So the network benefit is 0 if nobody buys. And the more consumers buy, the benefit increases. So let's just assume it's a simple linear function. Okay? So this is our idealized model. We'll just assume kind of the simplest reasonable functions. So of course in the real world it will be more complicated. But you see that the intuition is still very nice. Okay? So we have now the price is the product of R of z times f of z. And if you take those two functions, 1 minus x and z, and you multiply them, you get z times 1 minus z. So that's like an inverted parabola function. The maximum is 1/4 at z equal 1/2, and it goes to 0 at 0, it goes to 0 at 1. Okay? So this is idealized. In real world, it's going to be different, but still it's similar. It's going to go higher, and then it's going to go lower. Okay? So let's analyze, let's take a look at this nice curve here. Okay, so P star is the price. So for each value of P star, there's two intersections. At least if P star is less than 1/4. If P star is less than 1/4 and bigger than 0, there's going to be 2. Now there's 2 equilibria, not 1. Remember in the previous curve, there was 1 equilibrium, supply equals demand. Okay, that was the regular mark. But now things get more interesting. There's 2 equilibria. And also there's the third one, which is z equals 0. So there's actually 3 equilibria in all. 0, z prime, this intersection, and this one. So this system is going to be sitting either here or here or here. So the adding of the network effects gives you this extra equilibrium point. Okay, so that's kind of interesting, huh? Notice if P star is bigger than 1/4, if the price is too high, then 1 bigger than 1/4, there will be no equilibrium because there's no intersection. Huh? So it has to be between 0 and 1/4. Huh? So there's 3 possible equilibrium values. Isn't that interesting? So we go from a basic economy, when you have just supply equal demand, but if you add network effects, now you have these 2 equilibria instead of 1. So let me make the picture just to contrast it. Okay, so in the base case, you have this. R is increasing, and you have a price, P star, and you have an equilibrium, X star. So this is the equilibrium when you have no network effects. But if you add network effects, it adds this funny non-linearity, and it means that there's like an extra equilibrium that comes in. Okay? So that's interesting, huh? But it actually gets even more interesting than this, because now we can start talking about stability, instability, and tipping points. Tipping point is something you hear a lot of in the media when people talk about climate, stable climate. Well, actually, you could probably apply this to climate, huh? And you can see what's going on. So let's explore this now. This example of a simple network effects model. Okay? Assume that some fraction will purchase, but it's not one of the equilibria. Maybe it's like here. Maybe there's a value here. So what will happen? Okay. Well, actually, the R times RZ times FZ is going to be less than P star, right? But this is actually the condition for buying. The condition for buying is RZ FZ is greater than equal to P star. So a consumer will only buy if this condition is true. So if the Z is here in between, RZ FZ is going to be less than P star. That means they will not buy. So that means the number of buyers is going to decrease. This is called downward pressure. That means the number of consumers is going to go left and left and left until it ends up at 0. Okay? Assume now the second case. Let's say that there's consumers in between Z prime and Z double prime. Here, for example, RZ times FC is now greater than P star, which means yes, they will buy. And more buy. And the ones to the right will also buy. So there is upward pressure. So the number of buying consumers will keep going up until it reaches here. Okay? So this equilibrium is what happens when you have some number in between. It will keep going higher until it hits this one. And if it's even higher than that, again, the RZ FC will be smaller than C star, so it's going to have a tendency to go down again. So you can see, I made little red arrows to show you the direction. You can see Z double prime is stable. That means if there's a small fluctuation, it will go back. Whereas Z prime is unstable. Any small fluctuation to the left goes down to 0. To the right, it goes up to Z double prime. Z double prime is a very interesting point. It's called a critical point. It's also called a tipping point. A point de basculement, it tips. So if you go to the right, you will go up. If you go to the left, you will go down. So this is a very critical place. You see that? And this happens because of the network effects. It's interesting, isn't it? Okay. 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 Now you can actually do some kind of analysis. So if P star is set below the cost of production, the firm is losing money. Okay. If P star, so now you have to see what a company is going to do. Okay. P star is the price that the company sets. Okay. P star is the price. So the company sets this price, and this is usually the cost of production. But maybe the company wants to set a lower price or higher price. Okay. You see, if it sets a lower price, the tipping point is going to be more to the left. You see, this unstable tipping point is going to go closer to 0 if you lower the price. Huh? And if you higher the price, the tipping point will get higher. That's actually very interesting for a company. If you lower the price, the critical point Z prime will move to the left. And that means it's easier to get past it, because you have to get past it. Huh? If you stay to the left, you will converge to 0, and nobody wants that. So you have to get higher. Okay? So if you lower the production cost, then it's easier to get past it. And once you get past it, you're good, because then you converge to the higher one. Of course, also, if you lower the P star, the high equilibrium will also increase. Okay? Now, there's another effect. If you lower P star, the company might lose money. If I lower the price of the mobile phone lower than the cost of making it, I'm losing money. But maybe I want to do this Because if I do this, I will lower the critical point, and as soon as enough people buy the phone, it will go up, and then I can achieve the high equilibrium. So early losses, they can be used to maybe to achieve that high equilibrium. You see how it works? Later profits can offset early loss. So maybe you want to lose money early on to get past the tipping point. In fact, many companies are doing this. They give you free trials. They give you introductory prices. You see it all the time. The reason for this is they want that critical point to go low. They want to go beyond it. Okay? Okay, so that's our second model. So you see it's already interesting, huh? With the tipping point. But the second model does not show you enough of the dynamics. I'm going to now add something to make so that we can see really how things evolve over time. In the second model, yeah, we had upward and downward pressure, but we're still only looking at these points here. But now I want to have some idea of how it's going to evolve in time. Okay? And therefore I'm going to introduce a third model, and this will introduce another idea, which is a wrong belief. I'm going to make the model a little bit more sophisticated, and this will help us see how things evolve in time. Okay? Okay. In the previous model, we said consumers know that there's a fraction Z. Okay? And they know, and this is correct. They are correctly assuming that 90% of the users are using Office. Okay? But that might not be right. And in the third model, we're going to change it. In the third model, we're going to have two numbers. We're going to have what everyone believes the fraction is, and we're going to have what the fraction really is. Okay? We're going to say consumers believe that Z are using the product. They believe 90%, but in real life, it's only 80%, for example. And so the Z is going to be what the consumers believe, and the Z with the little hat here, the Z hat is going to be what the real fraction is. Okay? Okay, so the equation is the same. The consumer X wants to buy if Rx times f of Z is greater than 2p star. And Z is what they believe. Okay? They will buy, they make their own decision with what they believe. But the real value might be different. Okay? The real value is not this Z, it's another one, Z hat. Okay? The real one is this. It's the value of Z such that RZ hat times f of Z is equal to P star. Okay? So Z will be then equal to Z hat. So it's actually RZ hat times FC hat is P star. So you can actually compute from this formula what the real value is. It's the inverse of R of P star divided by f of Z, okay? So Z is what the consumer believes, okay? And Z hat is the real one, huh? So the consumer believes this, but the real one is this. This is what the real equilibrium is going to be, okay? So Z hat can be computed from the shared belief. Okay? So all the consumers believe it's Z, but it's not Z, it's Z hat. Okay? But that Z hat satisfies this equation. Of course, this one in practice it's very hard because nobody really knows these functions. Okay? Otherwise consumers could kind of cheat. But nobody really knows. But we're looking at the theory of it here, right? We can compute Z hat from the shared belief Z, okay? And from this Z hat, and then we can actually understand how things will evolve in time. Okay? Okay, but let me maybe, so we're going to study now what happens. We're going to use this equation, the real fraction, as function of the believed fraction, and we're going to use this equation to look at what happens in time, okay? And it'll give us even more intuition. But let me first make a break. Continue now. So now we're in a model where we have two fractions. The consumers believe that 90% are using Office, but it's not the real number. The real number is some other number. And if we know, according to the model, then the consumer will buy if this equation is true. So consumer X will purchase if this one is true. And if the fraction is Z hat, then this will be true for all the consumers that buy. So Z hat can be computed from this, okay? So we can actually compute it for our model. Remember we had our little model where we have R of X is 1 minus X, and Z is Z. We have this model. Well, let's compute this Z hat function. And this will give us some really good intuition how things behave over time, okay? So let's compute this. And so here's one slide where I'm basically doing some algebra. So this is an algebra slide, okay? I want to compute the Z hat in the case where R of X is 1 minus X and F of Z is Z. So I'm assuming R of X is 1 minus X. This is our little example, right? Is Z. And I want to compute Z hat, which is inverse of R P star divided by F of Z. Okay, I want to compute this. So this is, I'm going to call this function G. Okay, I'm going to call this function G of Z. First of all, there was only going to be a solution when P star over F of Z is less than or equal to R0. Okay. Why is that? Well, if you look at the R goes from R of 0 to R of 1. So if the P star is, so if the argument, so the inverse function is going from here to there, okay? This inverse function is only defined here. If the argument is too high, then there's going to be no inverse. So the Z hat only exists when P star over F of Z is less than or equal to R0, of course. Otherwise, we're outside of the range of R. Okay? So we want to know this function, G of Z. So this is our function. I will call it G of Z. It's equal to this when the condition is good. Otherwise, it's 0. So if I'm outside, I'm just going to say that the real valid fraction is 0. Okay? So either it's this number, if I'm inside the range, or it's 0. That's reasonable, huh? If the price is too high, it's just going to be 0. So what is G of Z? So we know R of X is 1 minus X. We know F of Z is equal to Z. Okay? So R, the inverse of R, is also 1 minus X. You can see that, huh? That the inverse is 1 minus X. So this is 1 minus X. So the inverse of R is also 1 minus X. R of 0 is equal to 1. So this condition here becomes P over Z is less than or equal to 1. So that's Z has to be bigger than P star. So P star is some limiting fraction here, in our model. And if you fill these numbers into this, you get this function. 1 minus p star over z, when z is greater than or equal to p star, otherwise it's 0. So you get this function here. So horizontal axis is what I believe, so the expected fraction, what the consumers think, and the real fraction z hat is here. So this is the function g. It starts being 0, but when the z gets big enough, then it goes like this, okay? This is for our little model. Huh? It's our model with the parabola. It gives us this function, okay? And now let's study this. This gives us an interesting kind of study, okay? So the expected fraction using the product is here, and the real fraction is here. Okay? Let's actually look at this and compare it to the diagonal, z hat equals z. Assuming z and z hat are the same number. Okay? And these two intersections are actually the equilibriums. Okay? The self-fulfilling expectations equilibrium, as before, in fact. These are the parts where the belief and the reality are the same. When z hat is below this line, like here, for example, when z hat is underneath this line, so z hat is the diagonal, there's a downward pressure. Okay? The real fraction is less than what the consumers believe. That means, since the real fraction is less, there's actually more consumers buying than what they should, and so some of those will be unhappy, and so there will be less and less. Okay, this is kind of like a convergence. The consumers are buying using z, but if the real fraction, z hat, is less than that, there's going to be some consumers that are unhappy, because they're going to realize that they made a loss. Okay? So there's kind of a downward trend here. So here, and actually there's z it's trending down. Okay? When z hat is above this line, that means there's less consumers actually buying than that they could buy. So some of the consumers that are not buying will realize they could have bought. Okay? So there's going to be like upward pressure. Okay? The outcome over, so there's upward pressure on z. So there's the z is going to change over time. See that? So you have the real value and the belief. So the belief and the real value, depending on how they relate, the belief is going to change over time. Okay? Either going up or down. And this function is the one we got for our simple model. In real life, you also have kind of an S-shaped curve, okay? Remember, our curve was like this, It was like a sharp change in direction. But in real life, not in our simple model, but in real life, it's also going to be kind of like this, okay? So the intuition is going to be holding, in fact, okay? So let's take a look now at what happens. The dynamic. Let's see how things happen over time. So now we're going to see how the consumers will change their behavior over time. Okay, so here's an example, a scenario. You people are on social media, on Facebook. Okay, each person has their own interest, which is R of X, their own cost paid for that. But there's also the attractiveness of the site itself. The more users that Facebook has, the more attractive it gets. Okay, that's f of z. Okay, there's also the effort of using the site. So this is like the price. Price, you're paying money, but you're paying like effort. Okay? So for Facebook, you can kind of use it like this. The consumer This is their own personal price. This is the benefit from all the fractions, and this is the effort it takes. So if the total benefit, RxFC, is bigger than the effort, they will participate. Okay? So this is how you can kind of put a social media into this economic model. Huh? So now the price is not really money, huh? It's the effort. Okay? Okay, so let's now look at how Facebook evolves over time. And to make it simple, we'll have time periods. T0, T1, T2. So initially, time T0, you have some initial audience size, Z0, okay? And then you see how this evolves, okay? So you can see we're going to model the social network using our economic kind of model. Huh? See how it works, huh? Okay. Okay. So at time T0, the initial audience size is Z0. Okay. And assume people, they know it. Okay. In each period, people will see, they will evaluate whether everything is fine. Okay. They will evaluate whether to keep going. So did everything good? Did everything work out the way they wanted? They didn't pay too much. So they will evaluate whether to go on. Okay? So in the first, time T0, the audience size is 0. In time T1, so people try to think of the future, huh? You see, people are estimating. And they think the future is like the past. Okay? So the people expect Z0 in time T1, which is the same as time T0. They expect it to be the same. But the real number is going to change. The real number, Z1, will be G of Z0. You see? So we're assuming people are just using it and saying, 50%, it's nice. And that's what they expect. The Z0, but the real one in period 1 is going to be Z1. There's like a delay, you see, between what the consumer is expecting and the real world is a little bit ahead of the consumer. Huh? You see how it works? And every period it's like that. So in period T2, well, the consumer eventually figures out that there's Z1 in period T1, and then they expect period 2 will also be Z1, but the real world is always going to be a little bit ahead. But then the consumer eventually figures it out. So that's like the time periods. Huh? So you have what the consumer thinks today, but the real social network is going forward. Huh? It's doing its thing, and there's no way the consumer can really know that until later. Okay? The consumer can only know the way it was before. And in general, we have Zt is equal to G of Zt minus 1. Okay, so this is our time step model. You see how it works? So we're assuming there's a kind of an offset, a décalage in French, between what the consumer expects and the real social network, which is already doing something different. And it's the G function which in our model will tell us what the different things. Okay? Of course, so this is an approximation of real life, huh? But still it gives us some interesting intuition. Because we have a model, we can actually, it's like a God's eye view. Huh? The model tells us everything. Of course, it's simplified, huh? But in the model, we can actually get a good intuition. So people will expect the future to be like the past, we're assuming. Well, they don't really think how it's going to be changing, but this actually is reasonable. You can see. Okay, so with this model, we can actually make some predictions. We can see with our function now. Okay, so this line, this heavy line, is the G function. It's the Z hat. So Z is horizontal, and the z hat is vertical. Okay? So we started at z0, okay? So we're here, let's say, in the beginning, huh? Now, the real social network is going to be doing at z1, and eventually the consumer figures it out. So we're at z1. So you see how it works. It's graphical, right? It's like zigzag. You go up until you hit the line, and then you go horizontal. So in the beginning, we're assuming that z0, the consumers know it. The social network evolves, so it goes to z1. And then, eventually, the consumer figures out it's at z1 now, but then it will go on again and so on. So we have this zigzag path. Okay? We can now use a graphical, we can follow our model graphically. So this is a really powerful way of understanding the system, using this kind of a graph. Okay? And here is more zigzags. So how does it work now? Well, it depends on where we start. Okay, we can determine the stability and instability by tracking the zigzag. And it all depends on the starting point. If we start here, below, then we will go down and to here. That means the real z hat is going to be less, and eventually the consumer figures out it's less, and then we get here. But when the consumers are at here, the real social network again will be evolving, going to here, and then the consumer, so the zigzag will go down that way towards 0. Okay? So this lower intersection is unstable, because if you're below it, you go down. If you're above it, like this 0, z0, z0, the social network evolves to z1. Eventually the consumer figures it out, it's c1, z1. But then the social network is evolving to z2, and so you have a zigzag which goes to converges to that upper point. So this lower intersection is unstable, and you can see how things kind of zigzag their way to the stable points. Okay, it's nice, right? So this higher intersection is stable. If you're higher than it, you will go down, but you will stop there. So you can see that this lower intersection is unstable, and the higher one is stable. Okay? That's interesting, right? Isn't it? And if you're a company, this can help a lot in how you do things. Okay? So here's, for example, a company. How would a company? So the problem, of course, is this lower point. Huh? The problem is here for a company. If the fraction using is less, it goes to 0 and the company goes bankrupt. But if the fraction is higher, then it goes to this very nice equilibrium and the company is surviving and making money. For a company then, this is a very important thing, this critical point, this first unstable point. Okay? Okay, so how does an industry or company do this? How can a firm that wants to sell a product with network effects use these insights to market its product? Now, supposing I'm selling a new software, hardware, whatever, I have to get past the tipping point. This is the lower point. It will not succeed unless you get past Z prime. You cannot start small and hope to grow. That doesn't work. So if any of you want to create a company, remember that has network effects, remember that, okay? You cannot start small. You have to get over that tipping point. So the trick is you have to convince an initial group of people to use your product, to adopt it. And enough so that it's past the tipping point. And one way of doing that is to set a low price, introductory price. Maybe you give it away for free, although that's also dangerous, but maybe. This will mean you lose money, okay? But, so your investors will be paying and the money is lost. But it's you're predicting that you get past the tipping point. If you get past the tipping point, then you can raise the prices, and then maybe you can converge to the higher stable points and overcome the initial losses if you grow. Okay, that's one way. Another way to get a large, so low price. Another way is to identify fashion leaders, or on the internet called influencers. So if some random generic celebrity person, Kim Kardashian, or if Elon Musk starts using some kind of aftershave or something, all the Elon Musk fanboys will buy that one, okay? These are called influencers. And in order to do that, you have to know who are the influencers. So this actually also is something we studied in chapter 19. This depends on the network. So if you know something about the network, you can use it to figure out who are the influencers, and the influencers people will follow them, and you get over this tipping point, okay? Okay, so that's already interesting as insight, Okay, we can also say something about social optimality. So again, I want to make the connection with the game theory and how the whole payoffs, all of the payoffs work for society. So what does network effects do on that? Remember, in the original model, the first one, the base model, the equilibrium is actually socially optimal for this one. We saw that for the break. But if you add network effects, it's not anymore socially optimal, in fact. Because the consumers are not independent. If you add a consumer, you will affect everybody. All the consumers will be affected. Okay? So how can you see it? So let's say we're at equilibrium, Z star, and the consumer with name Z star is like the highest one, R Z star times F Z star is P. Now the consumers that are a little bit higher, okay, a little bit higher than Z star, they will not want to buy normally, okay? They will not want to buy because this will be supposedly less than P, no? So this is like the edge. But if they did buy, if these guys who were a little bit higher than Z star, if they did buy, then everybody would benefit, even the previous ones. All the value of all the earlier consumers would increase. Okay? All of it will increase. What that means is that you're not getting this. You're not getting this benefit. Okay? You're not getting it with the network effects. So, in fact, you're less than socially optimal because of this. You're not getting it, okay? So, the network effects means you'll be kind of less than socially optimal. Okay, so that's kind of a comment you can make. Okay, let me make now another, give you some more intuition. What if you have more than one company, and they're competing? And they're competing, and the products all have network effects. Okay? So Microsoft was competing against a whole bunch of other companies. Most of them got broke, except Apple is still around. But there was lots of companies in the olden days making their own kind of PCs. Or their own kind of, there was digital research and CPM. You ever heard of that? No, I read an article in the 80s where it says, digital CPM has more than 1 million users. It will never die. You ever heard of it? No, so it's dead, right? So Microsoft remained. A few remained, like Apple. Apple and Microsoft made good. Most of the other ones, they disappeared. And there was another thing. This is videotape. You don't remember videotape. That's several generations in the past. Videotape was superseded, DVDs superseded videotape. And then we got Blu-ray, but now people just download and use Netflix, okay? So, but you can still buy DVDs. But in the 1980s, there was videotapes. You ever use the videotape? People sometimes still use it. There was actually several standards, VHS and Betamax. You ever heard of Betamax? Maybe you heard of VHS. Betamax died, okay? So what happens is, if you have a competition with network effects, one product will dominate and the other will die, okay? The product that first gets over its tipping point will be the winner. So Facebook is the most used social network. There used to be other social networks, MySpace or and other ones. Have you ever heard of those? Other, I don't know. There was a bunch of them. They all died because Facebook was the first one that had enough users. They got over their tipping point. So being first is much more important than being the best. So remember that if you want to make a company, don't try to make the best product. Try to make the first product, okay? So if A dominates over B, what can B do? B is doomed, right? Well, maybe if B is massively improved, and A is like doing nothing, then maybe B can overtake A. For example, Nintendo was a big one in the game console industry, and Sony has its PlayStations and so on, and then Microsoft comes in with this Xbox. They were nothing, okay, Xbox. There was Nintendo, there was Sony. So what does Microsoft do? Well, they start selling their Xboxes very low price, and they pay software companies to make really nice games. So they invested a huge amount of money into this Xbox, and it worked, okay? Or you can also compare Microsoft and Apple. So Apple managed to survive and do very well because they found another market, in fact, okay? But usually it's not going to happen like that. Okay? Usually you're dead if you are not the first. Okay? Okay, so that's something that you see there, right? So this tipping point is very important. Okay, now I want to go even farther. I want to give you a fourth model with even more intuition. This is the most realistic one, where you have population effects, like we saw before, but also individual effects. Okay? So in this case, now we assume the product is also useful if there's no users. Okay? In the previous model, the third model, we assumed that the product is useless if there are 0 users. So f of 0 is equal to 0. But now we're going to assume f of 0 is bigger than 0. Okay? So previously we assumed that if there's 0 users, it's useless. And this is true for telephones, okay? Alexander Graham Bell and so on. If you're the only one in the world who has a phone, it's useless, okay? But for a word processor, it's not true. For Microsoft Word, if you're the only one, it's still useful. So we can now assume that f of 0 is greater than 0. That means it's already useful if you're the only one, okay? And you keep that f is increasing. This will give us even more intuition, and you can see this will give us new phenomena. This will add another new stable equilibrium, in fact. Okay? And this will make a firm able to grow its audience from 0. So if your product already has value with 0 users, then you don't have to worry so much. So it's very good to make products that have actual value, even for 0 users. Okay? Okay, so let's make now a model of this. Let's define a new function. So f of z is not going to be z anymore, because here we have f of 0 equals 0. Let's say f of z is 1 plus a times z squared. So this starts at some value 1 and it goes up. and r of x is 1 minus x. So again, we pick simple functions so we can get the values. And we can figure out our z hat, our g of z, as before. So you can do some algebra. So I really recommend you do that, figure it out, and you should get this. So g of z is now 1 minus p star divided by 1 plus az squared. Okay? So we get something like this. And so let's take a look at that function now. So I'm really recommending you do that as exercise, so the algebra. Okay. This is what the function now looks like. Now it's kind of like this. Instead of starting like 0 and going up, it starts a little bit higher than 0. And now we have already an intersection here. And then we get our tipping point. And then we have our higher one. Okay? Okay, so again, this is z hat a function of z. You can see that even for 0, z, if I think nobody is using it, there might still be a real fraction using it. Okay? And it's because it has value. Even if everybody thinks they're the only one, that everybody thinks it's 0, which is here, there might actually be more than one person because it has value. There might be little clumps of Microsoft Word users, even if they don't know each other, and that's here. And the curve looks like this, and if you make the intersection with z hat equals z, you can see there's now these 3 equilibria. Notice this one is stable. That means a company can actually survive by living here. So you don't have to worry so much about going over the tipping point. If you're making phones, this does not exist. But if you're making a word processor, you have already a stable equilibrium here. So the company can be here and already survive, and then it has time to figure out how to get here. Of course, it's still interesting to get past the tipping point, but maybe you don't need it to survive. Okay? Okay, so that's one thing. But you can actually do more. If you lower the price, then the curve looks like this. It makes this curve go up a little bit. If you lower the price, this curve can go up a little bit. But now there's no more intersection in this case. So this is actually really interesting. So in the previous case, there was 2 intersections, a stable and unstable one. And so you could go here, and here you have this unstable point. But now if you increase that, if you make the curve go higher up, and you can do that by lowering the price, okay? If you lower the price slightly to q star, less than q star, you get a new function, h of z, that is higher. And if you keep lowering the price, at some point that new function, h, does not intersect this line anymore. Now things get really interesting. So what happens? Well, if z is equal to 0, you have here. But now if you look at what happens using our zigzag approach, you can see that there's actually a little path here. There's a passageway. And you will do zigzagging in this passageway. And this passageway can be very narrow. So actually, you could stay a long time here. You could be zigzagging here a long time. So it's kind of semi-stable, but it's not stable. But it's actually very interesting because it's always moving up. Okay? It's always moving up. That means that if you are here and you stay like this for a long time, this might take a long time. Eventually, you get past the narrow passageway, and schluck, you go up to the highest, the high equilibrium. You can see, instead of converging to the stable or having then a tipping point that is like a barrier, you actually have a passageway. And the only problem is, because it's narrow, maybe it takes a long time to get through, but you are always moving in the right direction. So you can see that it's very good to have a product that has initially already some value, and you lower the price. If you do it right, you will have this passageway, and if you can stay like that for a long enough time, you will eventually end up at the high point. So that's very good, right? It's very good, actually, huh? So this tipping point turns into a passageway. So you can see how making this kind of formal model can really help you get an intuition, huh? And if you're making a company, remember that, okay? Remember that you can do like that. Okay, let me summarize, and then let me say something about power laws. So we introduced 4 models today. The base model, supply equals demand, no network effects. The second model, when you have this self-fulfilling, these equilibrium situations. And then we looked at the dynamic view, whether you have stable and unstable equilibria, and we figured out that you can have tipping points, okay? And then finally, we added the most realistic case where you can have already things that are useful for 0 users and network effects. This will add a new stable equilibrium close to 0, which is good. And it shows a way that you can go past the tipping point. If you lower the price, the tipping point can convert into a narrow passageway that will let you go all the way up to the high. Okay? So if you're making a company on the internet, remember this. Okay? Some of you are probably thinking of making companies. I know students who made companies. And this is a good advice. Okay? Remember this when you make your own company. Okay? Okay, so that's all I'm going to say about direct benefit. I think that gives you a good intuition. And so the ideal model, you can actually generalize to the real world. Let me now finish today by talking about something different, by talking about power laws and rich get richer phenomena. We know rich get richer, huh? Someone who's very rich, like Jeff Bezos or Elon Musk, tend to get even richer, okay? But this is a general phenomenon, in fact, which you can see also on networks, on the internet. Okay? Okay, so let me make a connection with what we saw already. Remember cascades, the information cascades and the direct benefit cascades, they happen because peoples are connected. Decisions depend on decisions by other people, either sequentially or because of network effects. Okay? It's because that people are connected. Now, let's also look at popularity. And we'll look at popularity of websites. And also, again, this popularity has some property because people are connected. It's very weird. Most people are unknown in the world. They only have a few people who know them. But a few people are globally known. Everybody knows Barack Obama, for example, but nobody knows Joe Slughorn, who is the sheriff of some small town in Arizona. I don't know him either. Okay? So there's this huge imbalance. And so let me say a little bit about that now. Okay? So we switch now from cascades to web pages. Popularity of web pages. So web pages are a usual thing, and it's nice because we can actually study them very well. And we can measure the popularity. When is a web page popular? Well, when it has a lot of inlinks, when a lot of people are pointing to the web page, then it's popular. And so we can say, we can ask a question. How many popular pages exist? What are the fraction of pages that have k in links as function of k? How many very popular pages are there? And so let's study it now. And it turns out this is kind of counterintuitive. And the model that works is called preferential attachment. So this again shows how things are connected, how the connectedness changes the world in interesting ways. Okay, let me first introduce a naive model for web popularity. Okay, this is like what statistics people will do. So let me put on my statistician hat. Okay, naive natural guess is that web page index are distributed according to a Gaussian distribution, right? The world is Gaussian. There's a mean, mu, and a standard deviation, sigma, and there's this probability density function, which is this negative exponential. Ta-da! That should be the answer, right? Normal distribution is everywhere, and of course we have something called the central limit theorem, which you have seen, right? Théorème de la limite centrale. You remember that? You've seen it? No? You haven't seen it. Well, I will summarize it for you. If you take a bunch of small random, some independent random numbers, and you add them all up, then you get a normal distribution by magic. But they have to be independent. If you have a bunch of independent random numbers, then you will, and you add them up, it looks like a normal distribution. So that automatically emerges when you add them up. So the normal distribution is very natural, right? Yeah, it is actually. If you measure things in physics or experimental science, you will get normal distributions very often. Okay, assume that each page will decide independently whether to link to another page. So that means the sum of the in-links is sum of many independent random quantities, right? The number of pages with k in-links should be Gaussian normal distribution and should decrease exponentially in k because it's exponential density. But this is completely wrong. This is completely contradicted by empirical studies. So it's not Gaussian at all. Not at all. It's totally wrong to think it's Gaussian. The fraction of web pages with k in links is proportional to 1 over k squared. So this is a power function. Huh? So it's not exponential e to the minus k squared. It's k to the power minus 2. It's a power. It's a power law with the k squared here. Or maybe sometimes the number is a little bit higher than 2. So 1 over k squared is very different from e to the minus k or e to the minus k squared. Okay? This is called a power law because the density is power function. And it goes down much slower than exponential. Okay? Okay? So let me say something about power laws. So the normal distribution dominates in the natural sciences. That's true. But power laws dominate when you measure popularity. So popularity is not the same as an experimental measurement. Okay? Power laws are everywhere. The fraction of telephone numbers that receive k calls per day is 1 over k squared. Some telephone numbers are extremely popular. For example, a hospital will be more popular than somebody's house. Okay? The fraction of books that are bought by k people, that's proportional to 1 over k cubed. Some books are very popular, like the Harry Potter series. Some books are very unpopular, like the privately circulated memos of the Slovenian Philological Society. They're not very popular. Okay? So it's like this. The fraction of scientific papers that have citations also is 1 proportional to 1 over k cubed. Some papers are very popular, like Albert Einstein's first paper on special relativity. It's a very popular paper, but some obscure mathematical result published in Russian by some obscure mathematician that nobody knows, it's maybe less popular, especially if the Russian is not a famous mathematician like Kolmogorov. Okay, so these are power laws. They're not exponential. Okay, power laws. And then, in fact, it's very easy to test. If you want to know if a function is a power law, just make a log-log graph. Log versus log. Because log of f is a linear function of log of k. If you have a log-log graph and it's a straight line, then it's a power law. Okay? So power laws are what happens when you have popularity. Here is a figure that shows the popularity of web pages. Okay? Here it's the in degree, so the number of inlinks to the page. And here is the number of pages. See, this is log-log. 1, 10, 100,000, 1 million, 10 million, 100 million. Okay? You can see this is pretty much a straight line. It gets kind of messy when you get to the very, very, very popular pages because you have kind of random fluctuations. Okay? It's approximately a straight line. It only breaks down for a very small number of pages. See, like 10 or 100 or 1,000 pages. It's not very many compared to the whole web. Then you get these kind of random fluctuations. But it's a pretty close to a straight line. How do we explain it? How do you explain that it's so straight over 8 or 9 orders of magnitude? How does it know here that it has to follow the same line here? How does it stay straight over so many orders of magnitude? That's kind of a good question. What is the underlying process? How come? Because nobody designed the web. This is an emergent property. This is what we measure. Popularity is like a property that we measure, but we did not design that. So how come it's straight? What is the process? It's a good question, huh? So it's not like Gaussian, where if you add independent random numbers, you get a Gaussian. And normally when you do experiments in physics, that's what happens. If you do many experiments, the errors are independent, usually, and you add them and you get some kind of a Gaussian. Fine, we know it, we understand that. But how can we understand this? This was a big question, okay? When the web started to become very big, when people saw this, they said, how come it's like this? What is the underlying process? Okay? So how come it's like this? And this leads to, eventually people kind of figured out why it's like that. Okay? And it's like this. Normal distributions come from many independent decisions, whereas power laws, they come from correlated decisions. So the decisions are related to each other. Okay? So independent decisions gives this exponential laws and normal distribution, whereas correlated decisions give this power law, which is a very different distribution. Okay? People have a tendency to copy decisions made by other people. People look at other people, and the model that works is called preferential attachment. Okay? This is the model that actually works for web pages. This is a model, but here's a simple model for creation of links. So we assume the pages are created in order, 1, 2, 3, up to 100 million. And when a page J, number J is created, it makes a link to an earlier page by choosing randomly between two actions, A and B. Either it picks a random page from among all the earlier pages. That's like the Gaussian idea. With probability P, it just picks a random page. But there's another possibility, the B. So with probability 1 minus B, the page does not pick a random page, but it picks the page that that random page points to. So there's like an extra level of indirection. It picks a random page, and it creates a link to the page that that guy points to. That means a page that is pointed to by many pages will have a tendency to get even more pointed to. Okay? So action B is the key. If you only have action A, it's like Gaussian. But you will actually copy the decision made by the author of the other page, I. So you don't pick randomly your link, you will pick randomly the person you're copying. That means very popular pages will be chosen a lot. So if you pick a page I randomly, and that page will tend to point to popular pages. So very popular pages will become even more popular. Okay? And if you use this model, and if you analyze this, you can see the fraction of pages with k links is proportional to 1 over k to some power. So it's a power law. The value of C depends on the probability. So it could be 1 over k squared, but it depends on the probability. Okay? So this is called rich get richer. The rich get richer model. You copy the decision of a random earlier page. The probability that you link to some page is directly proportional to the total number of pages that link to M. So the more pages that link to M, the more chance you will also link to M. Okay? Pages that are rich, so that have many links, tend to get richer. Someone who is popular will tend to get even more popular. Okay? And someone who is not popular will not get more popular. Okay? The popularity of a page grows at a rate proportional to its current probability. If there's a difference between two pages, a page that gets a small lead over others will tend to expand that lead. Okay? Whereas for independent random variables, the differences are cancelled out because they're independent. The central limit theorem means when you add up all these independent random variables, they kind of cancel each other, and what's left over is this Gaussian. But in this model, it's very different. The differences are not canceling, but they're amplified. Okay? Anytime you have some kind of a real-world thing, you will have this situation. The fraction of cities, for example, with population k, is proportional to 1 over k to some power. The number of copies of a gene in a genome is also a power law. Anything that's organic, it's real world, is going to be like that. Anything where there's like correlations is going to be like that. Whereas if it's independent, it will be Gaussian. Okay? Okay. Let me stop here today, and next week we will go to one of the main, really interesting consequences, which is called the long tail. In French, it's called la longue traîne. Okay, and this is a thing which really explains a lot for internet companies. Okay, so let me stop here today, and next week we will talk about the long tail, and also then the next topic of the course, and then we finish the course. So next lecture is the last one.
Okay, so I really hope to see everybody. I will also give advice on the exam. Next lecture. We have limited to